The Poiseuille equation. Part of your exam will be pronouncing Poiseuille in an appropriate way. I'm not sure that I'm doing it correctly. Anyway, the Poiseuille equation um, describes how different variables affect the volume flow rate. I won't expect you to actually calculate the flow rate, but I do want you to know how the variables are related to one another. So the equation looks like this. It describes the flow rate. That's Q, right? We've already seen that. That's in cubic meters per second, or maybe cubic centimeters or milliliters per second. By the way, let's just take a little aside here. Did you know that a cc, which you hear that, right? You have so many cc's of medicine or whatever, that's equal to a cubic centimeter, which is equal to a milliliter. Uh, so there you go. So Q is equal to pi times r to the fourth. R is the radius. I'll draw a picture here in just a second. Times a change in pressure divided by 8. This is the Greek letter eta times L. Let me write that up here. So it sort of looks like an N, but it has this extra little thing on the end. This is the Greek letter eta. I think we had a hurricane uh, named once called eta. Anyway, these variables, R is the radius. So if I have a pipe, looks like this, R is the radius of that pipe. Delta P, see, this should be a capital P, I'm sorry. Delta P is a pressure differential. So if I have P2 down here and P1 down here, if my flow rate is in this direction, if Q is in this direction, the fluid is flowing in that direction, that means that P2 is less than P1, right? We're going to move from high to low pressure. The pressure differential then, delta P, would be equal to P1 minus P2, just the difference in those two pressures. Eta is a measure of the viscosity. If eta goes up, that means that my viscosity is increasing, it's becoming stickier. And then L, of course, is just the length of the pipe. And so I want to know what happens to Q when you change these variables. And honestly, I think that most of these, maybe all of them, all of these relationships are fairly intuitive. So let's go through these. What you want to look at here is recognize where I have a direct proportionality, where Q is proportional to R to the fourth and P, and then where I have an inverse relationship, where Q is inversely related to eta and L. And where I have a direct relationship is if R, for example, increases, that means that Q increases. So if your pressure stays the same, if everything stays the same and your pipe remains filled, if you make that pipe bigger, then of course your flow rate is going to be bigger, right? As long as your pipe remains filled. Now you might think, well, if you make the pipe bigger, then the fluid isn't going to fill the pipe, but we're assuming that it does, that there's enough pressure there to keep the pipe full, and that our pressure doesn't decrease. Number two, if the pressure goes up, that means that Q goes up. The flow rate goes up. Actually, if your pressure goes up, then your fluid will travel through that pipe at a faster rate, which would give it a larger volume flow rate. So both of those are direct relationships. Then there are inverse relationships. If eta goes up, if the fluid becomes stickier, then that means that Q will go down. It's simply going to travel more slowly. It'll be more difficult to push that fluid through, right? Have you ever had a really thick milkshake? It's kind of difficult to drink that through a straw as compared to, I don't know, a soda, right? So think milkshake versus a Coke, that the viscosity is larger in the milkshake, so it's more difficult to cause that to flow through your pipe, which is your straw. And then if L goes up, that means that Q will go down. Have you ever tried to suck water through a very long hose? I have. We used to have a well at our home. We drank most of our water from the well for many years. And sometimes our pump would die on the well, and we would have to siphon water up out of the well through a hose. And so you would have, here's your well. It's very deep actually. And your hose comes out here, and here's a little 10-year-old Chad over here trying to suck water through that hose. Because the length of this is so long, in order to get any appreciable volume flow rate, I have to have a pretty large pressure differential. And my little 8-year-old mouth just couldn't pull that off. So it's very difficult to siphon any kind of liquid through a very long hose. Okay, so that is the Poiseuille equation, and we'll see a number of ideas relating to that. I do want to say one more thing, that notice that Q is proportional to r to the fourth. All of these are linear relationships except for this one, where I have this r to the fourth power. Now I want you to think about what would happen if I doubled r. If I doubled r, what would happen to q? By how much would it increase? Well, if I have a 2 right here, it's not going to be just doubling q, because I also have this fourth power. It's going to be 2 to the fourth over here. In order to balance this equation and make the right-hand side equal to the left-hand side, I have to have a 2 to the fourth here and a 2 to the fourth here. And 2 times 2 times 2 times 2 is equal to 16. So an increase of a factor of 2 in R will increase the volume flow rate by a factor of 16. That is called a, well, let's see, it doesn't have, it's a non-linear relationship. All of these others are linear, right? The relationship between R and Q, eta and Q, and L and Q, they're either direct relationships or inverse relationships. Direct direct relationship right here, and then I have inverse relationships right here. Direct, if one goes up, the other goes up. Inverse, if one goes up, the other goes down. Okay? But they're direct or inverse, and they're linear. But here we have a direct nonlinear relationship.